Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Okay, let's unpack this.
Let's do it.
When you and I, or really anyone, pictures a star dying, in a supernova, we're usually imagining just the most extreme, catastrophic event possible.
Ultimate cosmic destruction, yeah.
Right. A massive, completely chaotic mess. It's this expanding cloud of superheated debris. And I love the term astrophysicists use. They say it has a texture like a giant turbulent cauliflower.
It's a great visual, and it's accurate. That's the standard picture of stellar violence we expect to see.
But the sources you've shared with us today, they focus on this one astronomical object that it throws that entire visual model right out the window.
Completely, yeah.
It's called Pop 30. And this remnant, is the perfect visual opposite of chaos, it looks like. Like an explosion that was frozen right in the middle of the burst.
That's a perfect description.
It's not defined by swirling clouds at all, but by these incredibly long, straight, almost geometrically precise filaments, all radiating outward from one single point.
And this exploration, it's really a perfect example of connecting, centuries-old observations from the sky with the most cutting-edge computational physics we have today.
A real bridge between the old and new.
Absolutely. Our whole mission here is to figure out this paradox. How can a stellar explosion, one of the most energetic events in the entire universe, end up creating something with such incredible structural order?
Right.
So we need to figure out not just what happened to the star that created Pop 30, which was a white dwarf, but why the debris cloud it left behind looks so radically different from pretty much every other remnant we study.
So this is a deep dive into stellar failure.
It is, and how that failure, weirdly enough, became the necessary first step for creating this spectacular geometry.
And this is where it gets, for me, just genuinely fascinating. We're talking about physics on this immense cosmic scale with material moving faster than any rocket ship we've ever dreamed of building.
Unbelievable speeds.
But the key mechanism, the thing that explains Path 30's unique, precise shape, is the exact same principle of fluid dynamics that creates the classic, iconic shape of a mushroom cloud right here on Earth.
It's the same physics, just on a scale that's hard to even comprehend.
So let's get into it. Let's explore the really complex astrophysics that turned what should have been this violent explosion into a geometrically structured whimper.
A very beautiful whimper.
We really have to start with that visual contrast because it is so striking. It puzzled astronomers for decades.
For a long, long time.
If you pull up images of remnants from what we call typical Type Iax supernovae, that's the kind of where the star is completely obliterated. You see exactly what we're talking about.
The cauliflower.
The cauliflower.
Yeah.
Thick, churning, chaotic clouds of ejecta. It's the perfect image of massive cosmic turbulence and mixing gas. This is what's supposed to happen when a star completely and violently tears itself apart.
And you have to appreciate the energy involved there. A standard Type Iax supernova. I mean, it releases an amount of energy in milliseconds that's equivalent to what our sun will put out over its entire multi-billion-year lifetime.
It's just an insane amount of power.
It's incredible, and that sheer instantaneous energy churns up all the ejected material so intensely that any little bit of structure it might have had at the beginning is it's ripped apart. It's thoroughly mixed, and that's what leads to that characteristic chaotic mess.
And these are the explosions we rely on, right, as cosmic yardsticks.
We do. We call them standard candles because their brightness is so predictable, which lets us measure distances across the universe. But the debris fields they leave behind are anything but standard in their structure. They are, textbook models of total cosmic chaos.
But then you turn your telescope to Path 30, and it is just so distinctively lacking any of those chaotic signatures. It's not a cauliflower at all.
Not even close.
Instead, you get these incredibly long, sustained, straight filaments. They radiate outward from a central point. The researchers described it perfectly, I think. They said it's like the trails from a sparkler that had been frozen mid-burst.
And that appearance, right away, it signals a huge anomaly. For years, astronomers really struggled to explain this structure precisely because it defied all the standard high-energy supernova models.
The question must have been, why is there any structure at all?
Exactly. And how did it stay so straight, so linear across these vast distances and over so much time? What's so fascinating here is that we can trace Pa 30's timeline way back in history. We now know that the event itself corresponds to something that Chinese and Japanese astronomers observed way back in the year 1181. They called it a guest star.
So we're talking about almost 950 years of observation here, starting with ancient records and leading all the way up to the high-res images we have today.
That's right.
Okay, so if the event was observed back then, do those historical records tell us anything about what kind of explosion it was? Did it look like a normal supernova to them?
And that is a crucial piece of the puzzle. The historical records actually support the idea that this was an unusual event even back then. The brightness records from 1181, they indicate that this guest star, which we now link to Pa 30 with very high confidence, it was visible for many months, but this is the critical part. It never got as bright as a standard, fully detonating Type Iax supernova.
Ah, so it was dimmer.
It was notably dimmer. This suggests it had a lower total energy release, or what we'd call a lower peak luminosity. This observational fact is one of the key clues. The explosion was powerful enough to be seen from Earth, but it was not powerful enough to be one of these full-scale, star-obliterating events.
So the ancient astronomers gave us our first clue.
Right.
A dimmer, longer-lasting blast. And modern astronomers see the aftermath, a strangely geometric remnant.
Exactly. That 9-century gap between the observation and the final explanation really highlights how complex this problem was.
But the recent research, the work spearheaded by Eric Coughlin and his team at Syracuse University, that's what finally provides the unifying concept.
It does.
And the core finding is just. It's so simple and profound. The star tried to explode, but it didn't fully succeed.
That is the critical, transformative insight. The star did not follow the textbook. It was an incomplete blast. This wasn't just a misfire. It's a specific, recognized class of stellar death that creates the perfect conditions for this very unique, very precise geometry.
So the fact that the explosion was a partial event, a failure, if you want to call it that.
A failure is a good word for it.
That's what ultimately dictated the fluid physics of the remnant we see today. If it had been a full-scale Type Iax detonation, there would be no Pa 30.
There would just be another chaotic cauliflower cloud, and the star itself would be gone forever.
So the visual signature, this beautiful geometric order, is a direct consequence of a failure in nuclear physics. That's the foundation that explains this whole 900-year-old mystery.
It is. And to really appreciate the details of that failure, we should probably quickly walk through the standard Type Iax process first, and then we can see exactly where Pa 30 went off the rails.
Good idea. So where does it start?
It starts with a white dwarf. Pa 30 came from a white dwarf, which is the super dense, extremely compact core left over after a star like our sun runs out of its nuclear fuel.
And the classic story of a white dwarf is that it's supposed to be retired, right? It just sits there quietly, supported by something called electron degeneracy pressure, unless
it has a friend, a companion star. If it's in a binary system, it can start pulling material, like hydrogen and helium, from that companion.
It starts accreting mass.
Exactly. And when it gathers enough mass, it creeps closer and closer to this critical threshold called the Chandrasekhar limit. That's about 1.4 times the mass of our sun.
And once it hits that limit,
the core can't resist gravity anymore. The pressure and the heat becomes so immense that it triggers runaway carbon fusion deep inside the star.
And in a normal Type Iax event, that first little spark of ignition very quickly turns into what's called a supersonic detonation wave.
Supersonic is the key word there. It's a wave traveling faster than the speed of sound through the star's material.
Like a shock wave of fire.
A perfect analogy. That detonation wave just sweeps through the entire star in a matter of seconds, converting carbon and oxygen into heavier elements, mostly nickel-56. This process consumes the whole white dwarf, completely obliterating it and scattering all that newly forged material across space.
And that's what creates those chaotic debris clouds we talked about. The star is just gone.
Utterly destroyed.
But Pa 30 star took a different path. This is what classifies it as the distinct Type Iax supernova. So what happened to that detonation wave?
Well, in the case of Pa 30 and other Type Iax events, the initial nuclear burning did begin. It started near the star's surface in a process we call a deflagration. Think of it like a fast-moving flame front, not a shock wave.
So it's burning, but it's subsonic.
Yeah.
Slower than the speed of sound.
Exactly. And this is the crucial failure point. That subsonic burning front, for whatever reason, failed to transition into a full supersonic detonation wave that would have propagated through the rest of the star.
It lit the fuse, but the bomb didn't go off properly.
That's it. The burning front stalled, or maybe it was just too slow and inefficient, so instead of a complete stellar detonation, you get this partial subsurface explosion. The source material calls it a fizzle, which, is still a tremendously powerful event by our standards, but on a cosmic scale, it's a failure.
And the incredible immediate result of this fizzle is the real key to Path 30's geometry. The star itself wasn't destroyed.
That's the most important physical outcome. The star survived, a hypermassive white dwarf, profoundly shaken, partially burned, certainly changed by the energy release, but it survived that initial failed blast, and it is still sitting there, intact, at the very center of the remnant today.
Wow.
And this phenomenon, the lower brightness of the explosion and the survival of the stellar core, that is the defining feature of these Type Iax supernovae. They're rare, they only account for a small fraction of all the white dwarf explosions we've seen, but we're recognizing more of them as we get more data on these unusual ways for stars to die.
It's a spectacular failure, and it gives us this incredibly rare, detailed data point. But let me challenge the premise a little bit.
Please.
If the explosion failed, if it was just a fizzle, where did all the energy come from to launch this sustained outflow of material moving at 15,000 kilometers per second? That speed is just immense. That's vastly faster than the Earth orbits the sun. A failed blast shouldn't be able to generate that kind of power over a long time, should it?
That is a brilliant question, and it gets to the really complex transient physics that happen in the moments right after the failed blast. The energy source is a combination of that initial partial burn and the dynamics of the star that's left over.
Okay.
So when that subsurface nuclear burn happened, it created this massive, superheated, dense shell of heavy elements, mostly near the star's surface. But because the full detonation wave never happened, that heavy shell didn't just fly off into space cleanly.
Some of it fell back.
A lot of it expanded violently, and then, yes, a significant portion of it began to fall back onto the surviving core due to its immense gravity.
So you get a rebound effect.
Exactly. The failed blast creates this massive pressure wave that travels inward, bounces off the surviving, still intact core, and then rebounds as a hyper-fast, outward-moving shockwave.
Like a cosmic pogo stick.
In a way, yes. This intense shockwave, which is driven by the post-explosion thermal pressure and these fallback dynamics, it acts like a cosmic cannon. It immediately starts launching an extraordinarily fast, dense wind of that partially burned material out into space, and this sustained stellar wind, moving at speeds up to 15,000 kilometers per second. That is the true engine that creates the geometry we see today.
And we also know the composition, which I think is critical for what comes next. This wind wasn't just hydrogen, it was enriched with heavy elements.
Yes, absolutely. The material being launched at these hypervelocities was made of the very elements forged during that brief failed nuclear burn near the surface, things like iron, silicon, other heavy products.
So you have a tremendously fast, heavy, and crucially, a dense stream of material being continuously shot outward from the star that refused to die.
That's the perfect combination: hypervelocity, high density, and sustained duration. That sets the stage perfectly for the unique geometry, which is governed by some very basic but very powerful principles of fluid dynamics.
It really transforms the surviving white dwarf. It's not just a remnant anymore. It's become a perpetual high-speed fluid injector.
That's exactly what it is.
So let's make that transition then. We go from a failure in nuclear physics to a success in fluid dynamics. We have this surviving white dwarf. It's launching a wind at 15,000 kilometers per second. It's dense. It's rich in heavy elements.
Right.
When this dense, fast wind slams outward into the lighter, much, much sparser gas that's just sitting around in that area, the interstellar medium, that surface where they meet, becomes a physics laboratory.
It does. That interface is where all the action happens. It's where the characteristic sparkler structure of Path 30 is born. From this point on, fluid dynamics dictates everything about the remnant's shape.
And that meeting point, where the dense, fast stuff hits the sparse, slow stuff, it's not stable, is it?
Not at all. It's highly unstable. And that inherent instability is the absolute key to forming those long, straight filaments.
Okay, let's talk about that first critical instability, the one that connects this cosmic event to something we can actually visualize here on Earth. The Rayleigh-Taylor instability, or RT.
The Rayleigh-Taylor instability is a really fundamental phenomenon in fluid dynamics. It describes what happens when you have two fluids of different densities, and you have an acceleration force that's directed from the dense fluid toward the light fluid.
It sounds technical, but the idea is simple.
It is. If a dense fluid pushes into a lighter fluid, or if you have some acceleration force acting across that boundary, the interface between them becomes unstable, and the two fluids will try to mix in a very particular way.
And the classic macroscopic example that everyone knows, even if they don't know the scientific term for it, is the shape of a mushroom cloud from a nuclear explosion.
Correct. That iconic mushroom shape is driven almost entirely by RT instability. The intense heat of the initial blast creates this massive bubble of hot, low-density gas inside the fireball.
And hot air rises.
Right. It rises rapidly through the cooler, much denser surrounding air. In that case, gravity provides the acceleration, effectively pulling the denser air down and around the lighter, rising fluid. And that density difference, coupled with the acceleration, causes the boundary to become unstable and form those characteristic swirling shapes and the big fingers or plumes that make up the mushroom cap.
Okay, so if P30 is basically a colossal cosmic version of that, we have to address one key difference. In space, on this scale, gravity is pretty much irrelevant compared to the kinetic forces at play. So what force is replacing gravity to define that density interface and drive the instability?
That is the essential insight you need when you apply terrestrial fluid physics to astrophysics. In P30, the acceleration isn't provided by a universal force like gravity. It's provided by the relentless, sustained kinetic pressure of that outgoing stellar wind.
So the wind itself is the force.
Yes. The dense, high-speed wind acts like a piston. It's forcefully accelerating the lighter interstellar material out of its way. The rapid deceleration of that heavy wind as it smacks into the lighter gas, that creates the necessary conditions for RT instability to kick off right at that boundary. The inertia of the dense, fast-moving wind is so immense that it acts as the primary driving force, pushing into the static light medium.
So the energy injection itself is the accelerating force. The dense, heavy wind pushing the light ambient gas forward is what causes those initial fingers to sprout.
Precisely. The conditions at the boundary between the dense, fast stellar wind and the surrounding interstellar gas were just perfect for RT instability. You have a dense, heavier wind pushing forcefully and continuously into a lighter surrounding material. This interaction causes plumes or fingers to develop at the interface, and they stretch out into the material ahead of them.
And in P30, those are the plumes that grew into the long, straight filaments we see today.
They are the very same structures, yes.
But that immediately brings us right back to the central puzzle of P30. If RT instability creates these fingers, why are they long, straight, and sustained? In most supernova remnants we look at, those RT fingers might appear for a split second, but then they're immediately ripped apart and mixed into total chaos.
That's right. They're incredibly transient.
So if you just look at the physics of a normal explosion, all of this beautiful order should just break down immediately.
And that is the fundamental difference that makes P30 so important for us to study. We are witnessing a physical condition that is actively suppressing the subsequent processes that normally generate chaos. P30 stays orderly because something is preventing those fingers from being sheared apart.
It's the difference between a high-energy explosion that just immediately collapses into this disorganized turbulence and a continuous, sustained process that maintains that structure for 9 centuries and counting.
And this brings us to the key physical insight that the computational modeling uncovered. The preservation mechanism is the extreme high-density contrast between the two materials, and it's the effect that has on a second, usually dominant, instability.
Okay, you mentioned a second instability, the one that usually causes all the chaos. Let's name it and define what it normally does in a typical remnant.
We have to talk about the Kelvin-Helmholtz instability, or KH. It's another fundamental concept.
Okay.
Where Rayleigh-Taylor happens when fluids accelerate across a density boundary, Kelvin-Helmholtz happens when fluids of different speeds move parallel to each other along a boundary. This creates intense shearing and mixing.
The classic example is wind blowing across the surface of water, right?
Mm-hmm.
It creates waves.
Perfect example. That shear between the fast-moving air and the slower-moving water creates waves, which eventually break and mix the air and water together. It's a mixing instability.
So in a typical full-blown supernova, you get the initial RT fingers forming, but the extremely high velocities and the turbulent motions at the interface immediately cause KH instability to kick in.
Precisely. And KH instability just tears those RT fingers to shreds almost instantly. The material flows are so turbulent and they shear against each other with such violence that any structure is destroyed. That chaotic, turbulent mixing is what makes standard supernova remnants look messy. That cauliflower shape is often a direct result of KH instability tearing up the initial RT structures.
So chaos is the default state for a cosmic explosion.
It is.
Which means that for P30 to have this geometry, the KH instability must have been somehow suppressed or damped down. So How does a high-density contrast do that?
It's all about inertia. The wind that was launched by that surviving white dwarf was so much heavier, so much denser than the surrounding interstellar gas that the mixing instability, the KH instability, just never got a chance to dominate.
So it couldn't get a grip, basically.
It couldn't. The source material notes that the density ratio between the ejecta from the star and the ambient medium around it was extraordinarily large.
So it's like trying to shear a very dense, thick, cold syrup that's being pushed forward with tremendous force against extremely light, still air. The sheer difference in mass and inertia prevents that lighter medium from being able to quickly rip apart the heavier one.
That is an excellent analogy. The dense fluid has far, far greater inertia, and that effectively damps down the shear forces that would normally lead to that rapid Kelvin-Helmholtz mixing. The dense material just keeps plowing forward in a linear path.
And it wasn't a one-time push.
That's the other critical piece. The filaments were being continuously fed by that ongoing dense wind being launched from the surviving white dwarf. This continuous high-density injection was the preservation mechanism. It kept the fingers stretching outward and actively resisted the forces that would normally cause them to shred into chaos.
So the high-density contrast means the order persists. The ongoing injection of material means the structure is sustained over time. And that combination gives us Pan 30's visually stunning, distinctive firework appearance that can last for centuries.
And the computational work, the work done by Coughlin's team, it confirmed this beautifully. They used these very high-resolution 3D hydrodynamical simulations, which let them isolate the effect of the density ratio on how these instabilities develop.
So they could turn the knobs, basically.
They could turn the knobs. And their models demonstrated that when you input conditions involving extremely high-density contrasts, where the injected fluid is hundreds or even thousands of times denser than the ambient medium, you produce exactly these types of long, straight, sustained filamentary structures.
So the geometry isn't just some leftover accident.
Not at all. It's an active, continuously fed structure that's governed by very, very specific conditions in fluid physics.
What I find utterly fascinating is that the research drew this unexpected parallel to real-world, highly constrained experiments that were conducted right here on Earth, a long way from the core of a star.
Yes, the connection to declassified data from atmospheric nuclear tests is probably one of the most compelling plots of this entire study. It links fluid dynamics across these radically different scales, from the surface of a star to a test site in the Pacific Ocean.
And they look specifically at photographs from the 1952 Kingfish nuclear test. That was an event studied specifically for its atmospheric effects, right?
That's right, for fallout dispersion and things like that.
So what did those Kingfish photos show that was so relevant to a star that exploded centuries ago?
They showed that immediately after the detonation began, these striking filamentary patterns formed within the rising fireball. It was clear visual proof.
So it proved, unequivocally, that RT instability works the same way, whether your energy source is a stellar core or a nuclear warhead.
Exactly. The initial physics of density instability is universal. It doesn't care about the scale.
But the source material highlights the really crucial difference in how the two events evolved over time. The Kingfish test ended up as a mushroom cloud, while Pa 30 ended up as a sparkler. Why did they diverge?
The difference is timing, duration, and the nature of the energy source. The nuclear test is what we call an impulsive energy release.
A single instantaneous burst.
Right. A massive amount of energy in a fraction of a second, and then a very rapid drop-off in the driving pressure. So in the Kingfish test, while you saw those initial RT fingers form, the driving force quickly vanished. And the atmosphere's own turbulence, driven by those intense shear forces, rapidly took over.
So the KH instability won out in the end.
It did. Those initial filamentary patterns quickly evolved into the chaotic, expected, classic cauliflower shape, because the turbulence, the KH instability, rapidly dominated the structure once the initial push was gone.
But in PAL 30, the star survived.
Exactly. And that is everything. The continuous feeding of that dense stellar wind from the surviving white dwarf was the preservation mechanism. It wasn't an impulsive event. It was a sustained energy and mass injection that has been going on for centuries.
And that sustained pressure.
That continuous pressure maintained the high-density contrast, which allowed the RT fingers to just keep growing, keep stretching linearly, and resist the KH-driven turbulence that would normally morph them into chaos. It's the duration and the density of the driving force that allows this beautiful order to persist over centuries.
It is just a staggering realization. The entire reason Pa 30 looks the way it does is because the explosion failed in this very specific way, which resulted in a sustained, dense engine, the surviving star that just keeps feeding highly structured fluid outward for almost 1,000 years.
And this knowledge, it has implications that go far beyond just this one remnant. This mechanism where an extremely high-density contrast preserves RT-driven structure by suppressing KH mixing, it suggests that we might see similar filamentary structures, either transiently or perpetually, in other astrophysical phenomena.
Anytime you have very dense materials slamming into a lighter medium.
That's the condition to look for.
So we're talking about potentially identifying whole new visual signatures for other kinds of cosmic violence. Where else might this be happening?
Well, the researchers point toward events like tidal disruption events, or TDEs.
That's when a black hole tears a star apart.
Exactly. When a star gets too close to a supermassive black hole, the tidal forces shred it. Some of that stellar material gets swallowed, but a lot of it is ejected outward at enormous speeds.
And that debris would be extremely dense.
Extremely dense. And it's slamming into the much lighter gas that typically surrounds a black hole. So if the physics holds true, we might expect to see transient, straight, pan-30-like filaments being formed during TDEs. And that could give us brand new observational tools to understand the outflow dynamics from black holes.
So studying this one, rare failed stellar death, helps us map out the entire family of violent cosmic events. It transforms the 1181 guest star from a historical footnote into a working laboratory for stellar evolution and fundamental fluid physics.
It absolutely does. It forces us to reconsider what chaos in space really means. It shows us that sometimes, under very specific conditions, you can impose this incredible geometric order on events that should, by all rights, be utterly turbulent.
This has been an incredibly deep and just satisfying dive. We've really journeyed from a celestial anomaly, this guest star documented almost 950 years ago by Chinese and Japanese astronomers, all the way to the complex world of computational fluid dynamics.
It's a huge leap.
We've established that the bizarre geometry of Path 30, this stellar sparkler, isn't an accident. It's a direct result of a very specific kind of stellar failure, a Type Iax supernova.
And the synthesis is just so powerful when you lay it all out. The star failed to achieve a full detonation, right? That left behind a surviving dense core that acts as a continuous injector.
The little engine that could.
It really is. This dense, hyperfast wind slams into the lighter interstellar medium, creating fingers through the Rayleigh-Taylor instability. And crucially, that extreme density contrast between the dense ejecta and the light ambient gas, it suppresses the usual shredding mechanism, the Kelvin-Helmholtz instability.
Which allows those fingers to persist, straight and orderly for centuries.
Right, and this gives us a crucial, detailed data point about the universe's complex physics that a typical, full, chaotic explosion would have simply annihilated, wiped clean.
So what does this all mean for you, our listener, taking this new knowledge forward?
I think it means that our understanding of cosmic phenomena is always improving, even for events that happened centuries ago. But maybe more profoundly, it means we have to always be prepared to look beyond the expected chaos. We just assumed that high-velocity collisions in space must always result in uniform, messy turbulence.
It was the default assumption.
It was. But if high-density contrast is the key to preserving these long, straight geometric structures, what other seemingly chaotic cosmic events might be hiding underlying perfectly straight geometric patterns that we just haven't focused on yet?
You mean
Yeah.
you might not have been looking for them?
Exactly. Whether we're observing distant nebulae, or the material flowing between binary stars, or the outflows from massive black holes, maybe there are patterns there that we just haven't focused our computational models or our high-resolution telescopes on yet because we assumed they couldn't exist.
That is a truly provocative thought. It suggests that in the cosmos, sometimes the whimper of a partial stellar death leaves a far clearer, more precise signature than the ultimate bang of a full obliteration.
The physics of failure gives us the clear geometry of success.
It does. It really suggests we should always look very closely at the anomalies.
They often hold the clearest physical explanations.
Well, thank you for joining us for this deep dive into the structured chaos of a failed star. We look forward to exploring whatever other mysteries you bring us next time.